All right, so now we're getting ready to be able to learn how to construct molecular orbital diagrams for any arbitrary molecule. Again, this chapter is going to focus on molecules that contain main group elements. So that means basically ones that only use s and p orbitals for bonding. However, later on in the course, we're going to expand that scope to include molecules that include transition metals, okay? And so before we get to that point, I just wanted to go over some of the factors that affect the energy of atomic orbitals. Because we're going to be making molecular orbitals by constructively and destructively combining atomic orbitals, right? So atomic orbitals decrease in energy as the atomic number increases. And so decrease in energy means more stable, right? And why is this? This is because there's greater positive charge in the nucleus, right? More protons. As you go to the right on the periodic table, there's more protons. That's going to pull in those electrons closer, making basically a tighter electron cloud. And so you have more positive, negative interactions there. And so that's going to be net a stabilizing effect. So you can see that within any one orbital, right, if you look at 1s orbitals, 1s starting with hydrogen and then going to the right on the periodic table as you're increasing the atomic number. If you just stick with one orbital, like the 1s, that's going to get increasingly stabilized. So by the time you get to neon, right, those are core electrons. And in fact, they're core electrons by the time you get to lithium. But they're going to be increasingly stabilized the more positive charge you have there. They're really close to the nucleus and they're feeling all that positive charge. And the same trends are true for any orbital, okay? So you can look at the 2s and the 2p's. Notice, of course, the 2s's are higher in energy than the 1s. They're further away, right? And the 2p's are as well. If you look at boron, right? 2p, 2s, 1s. That follows your normal electron configuration rules that you learned in general chemistry. But what is particularly interesting and relevant to us will become relevant to us. And so this is a point that I will come back to while we're constructing these molecular orbitals, is that the lower energy orbitals, i.e. the more core-like orbitals, those orbitals are affected more severely by this trend, okay? And so you can look at the 1s, this slope, as you increase the number of protons, as you go to higher atomic numbers, is really steep as compared to the 2s, right, and 2p. And this kind of makes sense because the orbitals that are closer to the nucleus are going to feel this nuclear attraction effect the strongest, okay? And so these facts are going to help us determine where to put the atomic orbitals that we start out with when we're constructing molecular orbital diagrams in terms of their energies, okay? And so hopefully you all are familiar with the Aufbau principle and this concept of building up, right? That, you know, if you have a 7p orbital, that's going to be, you know, much higher in energy than a 4f orbital. It's further away from the nucleus. And in general, it follows this trend, which is reflective of the shape of the periodic table. You may remember that there are exceptions. You know, copper has a strange electron configuration that doesn't fit. There are various maybe tricks that you learn in general chemistry. If you have a half shell filled orbital, that might be more stable, and there is some truth to that. Those are mostly empirical. Really, the results come from quantum mechanics, and so it's sometimes hard to just tack on, you know, empirical theories on top of it, kind of like what we tried to do with VSEPR and the steric considerations. But you can see, you know, there are some crossing over points where the energy ordering of these different orbitals switch, and that's reflective of the exceptions in this kind of idealized case of the energy orderings of the atomic orbitals. So that gives rise to some of the exceptions in the electron configurations. For example, copper. There's others, right? Many others. All right, so now we're ready to actually go ahead and construct our first molecular orbital diagram. And we're going to start out with diatomic molecules. Now, depending on what background you have in general chemistry, some courses go over molecular orbitals. And for me, at least, that's actually a very confusing topic as a first-year chemistry student, first-year undergraduate. It's kind of just thrown at you. You're given the answer of these different diagrams, and maybe depending upon what your curriculum was, you're expected to memorize those orderings. The energy ordering can switch, and it seems sort of random and arbitrary and very mysterious. So when I first learned molecular orbital theory in a general chemistry class, I learned it in several general chemistry classes. I didn't really know what was going on. But now, because you know group theory, you have the foundations to really understand this at a much deeper level and from the ground up. And so I think that's going to be very powerful for you. And if you do remember some of these general chemistry principles of MOs, now you'll understand where those are all coming from. And there's not going to be any memorization associated with it. It's just going to be logic built up from kind of our fundamental principles, which is, always what you want, right? So anyway, we're starting with very simple molecules, diatomic molecules. These are the easiest MO diagrams to construct. And, we're taking a group theory approach here. So we're going to be identifying the point group. That's the first thing we're always going to do. Get a new molecule, we identify the point group. Then we're going to list the atomic orbitals that are going to participate in bonding. Those are going to be the atomic orbitals of the valence, that contain valence electrons or could contain valence electrons. We're going to list those in terms of their energy ordering, and then we're going to determine their characters. So we're going to determine their symmetry in that point group, right? Then we're going to form molecular orbitals from atomic orbitals. And the key thing that we'll always be harping on is that they have to have similar energy and they have to have same symmetry. If they don't have the same symmetry, they are orthogonal in symmetry space. And so their overlap integral will be 0. And you can't make a bond or an antibond between them. You can't make them an MO. There's no interactions. It's going to stay as non-bonding. Okay. If they're not of very similar energy, the intensity of that overlap integral is just going to be very weak, okay? And we saw that, right? If you have two atomic orbitals that are similar in energy, that's going to give rise to a greater splitting than if you have two atomic orbitals that are very different in energy. They're just going to change a little bit, okay? So we'll see these principles play out in many, many examples throughout the next 3 chapters. And then we're going to determine the characters or the symmetries of the molecular orbitals. And then we're going to populate the orbitals with electrons following Hund's rules. Remember, Hund's rules tells us basically what the ground state is when you have some options, what look like options, okay? So let's do, so I think I'll stop this video here and then we'll parse it into a separate video once we get to this example.